The Indian Institute of Science, Bengaluru, not only churns out excellent talent in the field of science and technology, but also develops innovative solutions to accelerate the scientific advancement of the country. One such innovative solution that the Premier Institute has come up with is the drop impact printing technology. The technology has been developed by the Institute's Center for Nano Science and Engineering and can be used for a variety of printing applications, including 3D printing of live cells. Let's see how this technology solves problems related to new age printing.
Printing technology has progressed a lot over time. From paper printing to design and 3D printing, and now manufacturing is also closely tied to printing. However, with the change in printing needs, traditional printers are no longer able to keep up with the ever-changing field. Printers typically have nozzles with small holes that cannot withstand high mass loading, and the nozzle becomes clogged. This poses a huge problem in bulk printing, 3D printing and bioprinting. To overcome this, researchers from the Center for Nano Science and Engineering at the Indian Institute of Science, Bangalore, have now developed a drop-on-demand or drop-impact printing technology that is capable of generating a wide range of droplet sizes using a variety of inks. This innovative technology developed by Indian researchers can open a new dimension in the field of 3D printing, conventional printing, and even in the field of bioprinting that requires dispensing live cells. The technology also promises to significantly reduce the printing cost.
In drop impact printing, we use the kinetic energy of a falling droplet on a superhydrophobic mesh to generate smaller droplets. The size of the ejected droplets can be controlled by changing the pore openings of the superhydrophobic mesh. This unique way of printing is economical and simple. Nozzle clogging is a major problem in most of the existing printing techniques. In drop impact printing, as the superhydrophobic mesh is used, it doesn't allow the falling droplet to stick to the superhydrophobic mesh, and hence in this particular technique we can print particle suspension with very high mass loading.
The new technology replaces the nozzles with mesh. Nanowires are grown on the mesh and the resulting is chemically treated to make it super hydrophobic or water resistant. As a result, when a large droplet impacts the mesh, it is repelled by the non-wetting surface and it bounces back. However, during the bounce back, a small part of the droplet breaks through the hole in the mesh and gets deposited on the surface below, and the droplet is printed. Since a large part of the ink is in contact with the mesh for a very short time, the particles do not get a chance to clog the pores of the mesh. This allows ink with more mass to be used. In a single cycle, lines as high as 217 microns can be printed, which may still require hundreds of printing cycles in a traditional printing machine. The idea of drop-impact printing emerged when researchers were working on the development of nanostructured surfaces that could repel water.
The question is, how does this droplet ejection take place? And more importantly, why does it take place during the recoil phase? Upon further investigation, we found that when the droplet hits the superhydrophobic surface, a cavity is created at its center. And when this cavity collapses, momentum of the interface is higher than the momentum of the actual impacting droplet. This leads to formation of a jet, and which breaks to give us a single droplet.
This printing technique is useful in various applications. Electronic circuits and devices can be printed on flexible substrates. 3D printing can be done using high mass loading ink, and printing of live cells and bacteria has also been achieved using this technique. As the setup is extremely simple, it reduces the cost, thereby improving the printer's accessibility to a larger community. The mesh also costs only a small fraction of the nozzles that it replaces. This significantly reduces operational costs when compared to conventional printing techniques.